Welcome back to CS 520. Today I'm going to talk about implementing an exception mechanism in C. And our mechanism is going to have a very simple interface. We just have three routines. The first routine, catch exception, just says that we're willing to catch an exception at this location in the program. Second routine cancels the last catch exception call we made. And the final routine is the routine we use to actually throw an exception. Note that the single parameter to throw exception is just an int. So our exceptions in this mechanism, in this model, in this implementation, our exception values are just going to be integer values. Also note that we can have multiple calls to catch exception alive at one time. In essence, you can think about them as sort of stacking up. And cancel catch exception gets rid of the last one. Let's take a look at, map this to an exception mechanism in a language like Java. So we think about having some syntax, which we don't have in our world right now. We're just using regular C. But you can imagine, having a try catch statement where we put the try around a block of code that we're worried about an exception occurring in. And if an exception occurs, we have a catch clause which executes and accepts the exception value and then can process it. Well, how does that kind of syntax map to the mechanism that we're talking about? Well, to do a try in our world, the programmer would call catch exception. And the tricky part is that catch exception will return twice in essence. The first time it returns, it always returns as 0. So when you enable the catch exception, when you call catch exception, the first thing that's going to happen is actually you're going to go down here and execute this block of code. And notice this block of code contains code block 1, which is the body of the try block. Okay, and if that executes successfully without an exception being thrown, then we will do a cancel catch exception to cancel out this catch exception, which was never actually used in this case because 1 executed all the way to completion. So what happens if an exception is thrown from block 1? Well, then catch exception wakes up for a second time in essence. And this time, when it returns to us, it returns the exception value, which in our world has to be a non-zero value. And then block number 2 from the catch clause over here on the left executes, and we can try to handle that or respond to that exception. So again, the tricky part in our interface is that catch exception in essence returns twice if there's an exception thrown while it's still enabled. Okay. It returns once and returns 0 so that we'll execute down here. And if that executes to completion, then we cancel out the catch exception. Otherwise, if there's an exception thrown in block 1, then catch exception will return for a second time, sort of magically, and this is what we're going to talk about how to implement. And then block 2 will execute to allow you a chance to respond. Note that block 2 could decide to rethrow the exception if the exception number is a number that it can't actually handle. Okay. And it's also important to realize that block 1 might include other try blocks. It might include function calls. The function calls might include try blocks, which is the sense in which I mean catch exceptions calls can sort of stack up, or that more than one can be active at one time. And the catch exception that responds is always the last one that was called. Similarly, when you cancel, it's always the last one that you cancel. So there's sort of a stack mechanism. There's a stack of these catch exceptions, and we'll see that as we talk about implementing this. Okay, so the key to understanding the implementation here is you have to understand how the Intel 64 stack frames work. So if you're a little hazy on that if you haven't looked at that for a while, you might want to go back and take another look at the Intel 64 architecture lecture. Remember, there's a runtime stack, and there's a stack frame for every executing function. And these diagrams, again, I guess I'm drawing the stack growing from bottom of the page up towards the top. So if we have a function f running, and f calls catch exception, there's going to be a frame for f, and there's going to be a frame for catch exception pushed on top of the stack. Okay, catch exception returns, it returns back to f, and that frame will disappear. So if that happens, if f calls catch exception, it'll return back, and then after some point in time, somebody throws an exception. In this case, I'm have a scenario where f called g after the catch exception call was called and returned from. G called h calls I, then inside of I calls the throw exception function. So at the runtime stack, we'll have a frame for f, a frame for g, a frame for h, a frame for I, and finally a frame for throw exception on top of the stack. And what we want throw exception to do is essentially magically return the stack to look something like this, as if catch exception had a frame on top of the stack, and then we're going to simulate it, catch exception returning for a second time. So the big task that we need to do is we need to pair the stack back, right? The stack pointer is going to be pointing up here at the top of the stack, and we want, in our implementation of throw exception, we want to bring the stack all the way back to here, reset up a frame, set up again a frame for catch exception so that it can return again back to f, and we can inform f that there's an exception has occurred somewhere, in this case up in function I. Okay? And notice when we return that second time, we need to return the exception value as the return value from catch exception. Okay. So the magic here is to pull the stack back and recreate this picture essentially right before catch exception returned to f the first time. So what do we have to do this? Let's look at each of the functions one at a time. Well, with catch exception, essentially we want to take a snapshot of the stack. I'll be going back to this picture all the time, right? Catch exception's running, we're looking here. We're looking here. And we want to sort of take a snapshot of what things look like here, because the goal is at throw exception, we want to recreate the situation. So I take a snapshot of what this looks like so we can recreate it over here. And in doing that, we'll pair back the stack. Okay. So we're going to take a snapshot. What does that mean, really? Well, it means we really need to grab the contents of key registers. Remember the frame pointer, which is called the RBP. It turns out we're going to need the RBP of catch exception itself, and we're going to need the RBP of its caller. We're also going to need to save the program counter, which on the Intel 64 is called the RIP. Okay, and our interface, the spec for our interface says that we should also save these other callee saved registers, RBX and R12 through R15. What we're going to do is we're going to store the contents of those registers into a struct. So we'll have to allocate a struct, grab these register contents, stash them into that struct for safekeeping. And there'll be one of these structs for every active call for catch exception. And again, since there can be more than one of these active calls, what we'll do is we'll stack them up. We'll keep a stack of these structs where the top item on this stack is the snapshot of the most recent call of catch exception. So let's take a closer look. Let's kind of blow up the first picture so we can get a better idea what exactly goes on with this snapshot. So the situation when we're in catch exception on the runtime stack looks like this. Again, I've got the runtime stack growing up towards the top of the page. Right, if you remember how this works, we have a current RBP, a current frame pointer that points into the middle of the frame on top of the stack, which would be the frame for catch exception itself. Because again, function F called catch exception. So function F has a frame, and when catch exception is running, it has a frame. And remember, in the middle of the frame, the key component here is there's a saved RBP. So that's the RBP of the caller, F, and also the saved program counter, the saved RIP. Right? This tells us where the frame pointer, again, remember it's a backlink. These frames you can think of them as being linked together by these saved RBP values. So this one points back to the middle of F's frame, and this is the return address to where we want to return, where we want to execute next, in other words, in F when catch exception returns. So the snapshot here is really we need to get the current, right? We need to get the current RBP value. We got to grab that and put it in a stack. And it turns out we're going to need to save this value and this value. So if we can get the current RBP value, it will point to the saved RBP value, and then 8 bytes away will be the saved RIP value. And notice that, again, stack growing up this way, that means this is a low address up here. Low address. And there's a high address here. So this address is 1 less, or actually since it's 8 bytes long, it's 8 bytes less than this one. In our implementation, we'll probably want to be thinking of long stars, right? In our C code, we'll probably want to be thinking of these things as a pointer to a long. So if we can grab the current RBP into a pointer to a long, then it allows us to manipulate these two addresses using that pointer value. And since it's a long pointer, if we just add 1 to it, it will scale this and point it to the next long in memory. And so we can grab these 3 values, stash them in our struct, and push that struct on top of a stack. Okay, and along the way, we need to also grab these other values and put those in the struct. Okay. All right. So that's one side of the coin where we take a snapshot. Let's look at throw exception now, which is when we restore things using that snapshot. Okay. So when somebody calls throw exception, we want to restore the runtime stack using a snapshot that we took that's on top of the stack of these structs. So we're going to put the snapshot into a struct we allocate, and we're going to push it on top of the stack. And when a throw exception is called, we just look for the snapshot that's on top of the stack. And in fact, we pop that stack. So one catch exception is used and discarded for one throw exception. Okay, so we restore the runtime stack. We have to restore the registers that we've saved. And then we have to somehow perform the second return from catch exception. This magical second return. Again, let's look at a blown up picture for the situation. Let's see if we can figure out how this is going to work. So again, the stack is kind of growing up here. F is where we called catch exception, and then we're hypothesizing here that we've had F called G after catch exception returned to it. It called G, it called H, it called I, and now I is calling throw exception. Well, remember that the RSP, the stack pointer, is going to be pointing to the top of stack. The RBP inside of throw exception will be pointing to the frame for throw exception. And what we want to do is we want to manipulate the runtime stack using our snapshot to create this, right? We want to recreate. This is sort of the recreation of the frame for catch exception. We want to put its saved RBP, what it had in its saved RBP slot, right? We want to restore that saved RBP slot, and we want to restore that saved RIP slot that it had in its frame for catch exception. Again, what happened to my detailed picture for that? right? It was this situation, right? The one we were just looking at, right? This is catch exception. When we took the snapshot, we saved these two values. We saved where these values are lying in memory, right? By saving 1, 2, 3 values, we can recreate that on here. Right? We know this is going to be the RBP that we saved, and then the two values that were pointed to originally, we're just going to restore them. And then how do we actually pair the stack back? Well, we reset the RSP register, right? It was pointing up here when we were entered, when throw exception was entered. What we got to do is have throw exception change the RSP, and bring it down to here. Okay. Then, if we just execute the normal return sequence for a function, that will, remember what the normal return sequence for a function, all good Intel functions do a pop quad word of %RBP, and then they do a return. Remember, that's what all good functions do. If we've reset the stack like this and then we execute that, we're going to restore the RBP of F, and the return will restore the instruction pointer of F, putting us right back into F as if catch exception was returning a second time, which is really what it's doing, right? So again, the important thing is we move the stack pointer from here to here after we've restored these values, and then we execute a normal return sequence for a function, and we get a pop quad word to restore the frame pointer for F and the return, which restores the instruction pointer for F. And magically then we're back in F as if catch exception had returned again. And of course the other thing we need to do is we need to set RAX. Right, we need to set RAX to the exception number, because remember, on the Intel 64 hardware, the return value is placed into the RAX register. So if in the course of things, again, we're talking about throw exception. In the course of doing throw exception, I'm going to pair back the stack. I'm going to reset these values, reset the stack pointer. And if I set RAX to be the exception value being thrown, again, that's the parameter to throw exception, then do this pop quad word RBP and this return. That's how I get the black magic. That's how I make it look like catch exception is returning for the second time, and now the exception number is the return value. Okay, pretty tricky stuff. You're going to need some assembly language code to do this. All right, we're going to need some assembly language code to actually be able to go out and grab those registers. Maybe, one way to do it, there's many different ways to do it, but one way to do it is have a separate routine that you call. It's only a couple lines of code if you think about it, to get the RBP, to get the RBX, to get R12, 13, 14, 15. Remember, what's the code for a function like this? It would just simply be move RBP into RAX and do a return. Okay, you wouldn't even need to set up a frame pointer. You can just grab the current frame pointer. Don't change it because you're trying to get the frame pointer of the caller. Just grab the current frame pointer, do a move quad word of RBP into RAX, and then do a return. And that will grab the RBP value. Okay? And you can do that for all these other registers. So a couple lines of assembler. It's actually more than a couple lines because you need to have the label for the entry point and all that boilerplate. So there's 4 or 5 lines of assembly code for each one of these. And you may also decide that you want functions to do, assembly language functions to do the reverse. Now you'll pass in a parameter that says what the value is for RBX, and then you'll set RBX to that value. Again, it'll just take a move quad word from the register that holds the first parameter, which is what? RDI. Think for a minute. It's RDI, right? It holds the first parameter. So you could write these set routines by just moving RDI into RBX, for instance, or R12 or whatever. Okay, so you probably have to have some mechanism to save registers and restore registers. And then you need code, probably a separate function that's going to do the magic, actually pair the stack back, restore the key registers, the frame pointer, reset the stack, set up and perform that second return from catch exception, putting the exception number into RAX. Okay, so you're going to need a small body of assembly language code. Again, it's not very much code, but it's tricky code. That's the challenge. All right, finally, what about the last routine? Well, the last routine is pretty easy. Cancel catch exception just means pop that stack of structs, right? Pop that stack of snapshots. Just get rid of the last snapshot, essentially. That's all you need to do. So that can all be done in C without any problem. All right. So tricky stuff. What you want to do is you want to go through this, maybe watch this video a couple times actually. Think about it, come to recitation with your questions, and we'll talk about it further there. All right, let's stop here.